Okay, so I would like first to thank Jean-Louis for the invitation and all the organization staff. And I apologize that you have not paper support, but you will have it soon. And just to present me briefly, or to present my university, because as you see, I'm from Université de Picardie Jules Verne, which is in France. You notice it due to my accent. So it is 100 kilometers north from Paris. And why Jules Verne? Because you all know Jules Verne. In fact, Jules Verne was born in Nantes, which is west of France, on the Atlantic coast, but quite young, 25 years old, more or less. He moved to Amiens, where he got married and worked for the city and wrote almost all his books there in Amiens. So if you go to Amiens, because Amiens, yes, sorry, it's not there. It's the place where the main part of the University of Picardy is. And if you go to Amiens, there is two things to visit. There is a very, very nice cathedral, considered in France as the two best cathedral. The other one is in Chartres. Maybe there is also Reims, but it's not as nice as Chartres and Amiens. And there is also a museum dedicated to Jules Verne. So if you are in Paris, send me an email. I will invite you to give a talk, and you will have things to visit. So now I turn to my talk. So it is a talk that will, these are two lectures that will lie in the intersection of computer science and mathematics. And before to explain what I will do exactly, I will start with motivations, okay? And at some point, I will show you Cobham theorem, which is a very, very nice theorem. So motivation, it starts with a question, simple question, that is typically a question in computer science. Take a set S, any, which is a general question. Does there exist an algorithm? Of course, as we have computers with finite memory, you ask for finite memory algorithm that recognize the element of S. Typically, it should exclude the prime numbers because I imagine, I'm not specialist, but when you are doing the Eratosthenes sieve, then you need longer and longer and longer prime numbers. And if you have just short memory, small memory, you should have problem. We will precise this later. So this is just the question, and Cobham's theorem will give some answers, because of course it's so general that maybe you can give a lot of answers. So subsets that you can think of are natural numbers, so the odd numbers, even numbers, prime numbers, powers of 2, anything you can think of. Even in higher dimensions, I put n, I could have put z, but there is no problem in what I will say later. In R2, interval, balls, curves. Okay? Even in fields, rings, groups. If you have your favorite object, take it and try to answer these kind of questions. Of course, when you ask this question, so you select, let's say, R or some field, you should have a way to represent your numbers. So you should, in order to answer the question, select a way to encode your elements. And so first restriction, I will use a numeration system. You could also use prime numbers or prime polynomials to encode your numbers or polynomials. So this is rather natural. And what do we mean? So I'm not specialist of algorithms. I imagine there is a huge list of different class of algorithms. But as I ask, finite memory, I think, but as I said, I'm not specialist, it excludes Turing machines. Okay? And what I will use are finite automata. Okay? So this is the setting of the framework of what will come now. Okay, so this should be clear for everybody. This is the starting point. And Koba made two observations. Observation, not observation, because as you will see, you will not see, hopefully. The observation is a series of more than 30 lemmas. So it's not an observation. So it strongly depends on the numeration base you will choose, which means that, we will precise this later, that if your subset is recognizable in some base, it should not be recognizable in some other base. We will precise this in a moment. Secondly, not the sets that are recognizable in the setting I said are very special. They are not all. Of course, the one we have in mind are the set of prime numbers all the time. But just let me show you an example. I could have started with the even number or odd numbers, because as for even numbers, in base 2, they should end with a 0, and you see that the algorithm to check whether it is or not an even number is just to read the digits. Or you can start reading from the left to the right, or vice versa, but if you start from the left and you read the digits to the right, you should end with a 0. When you end the lecture of the digits, it should end with a 0. But it is a kind of easy example. This one is not difficult, but is not as easy as the previous one. If you take the powers of 2, of course, we will choose base 2. You know that there are a lot of questions that when you have base 2 and base 3 to manage together, it is an operand problem most of the time. So here, you just look at that. So you write the expansion of the powers of 2, and it's a 1, and then some zeros. Then you should find an automaton. So I will almost give no formal proofs, just proof by examples. So consider this. So this is a typical automaton. It means you have states. These are the disks which are red and green. You have some arrows, maybe you don't see, that are going into some states, and some others that are going out. So those that are going inside the circles are those where you can start the lecture of your expansion. And where you have an arrow that is going out, it means that to be recognized, you should end there. So you can have several such states. You can have several such states. Okay? So let's just look at this example. Take a power of 2. So you should start here due to this arrow. So first, so I said we will always read from left to right. It is not a problem. When such automaton exists for the lecture from left to right, it exists from right to left. So I read a 1, and then I read some zeros. And if I am a power of 2, I will stop here. So I am recognized because the last state has such an arrow that is going out. But if I'm not a power of 2, then I will read some 1 necessarily. And then whatever I read after, I will never be a power of 2. So then here it is rejected. This is why there is no arrow that are going out. So such a set is said to be 2 recognizable, which means when I write this number in base 2, I have I obtain a language that is a finite a set of words here on the alphabet 0, 1. In this language is exactly all the finite paths that start here and end there. Exactly. One expansion of this set start here and there, and any path that start here and end there is an expansion of my set, of an element of my set. So if this notion is not clear, please tell me, because otherwise, right after, you should not understand. The concept is quite clear. Just elementary machinery called automaton, where the language of the set of the set is exactly the path that starts somewhere and end somewhere here. And remind you that I said that Cobham made the observation that it strongly depends on the base. So the question is, now write the expansion write the power of 2 in base 3. I think even this language is not known, characterized. You can ask, does there exist a finite automaton that recognizes the power of 2 written in base 3? So this is a language. You can take a power of 2, use the Euclidean algorithm, and you will obtain the expansion. So the answer will come later, but the answer is no. But just I continue with some examples. Something sometimes called the integer counter set. It means you take the integer which are in base 3, which in base 3 do not contain the digit 1. And it is exactly like the counter set. This one is also, maybe I can, it is an exercise. It is also recognizable in base 3 because it is just like that. So you start your lecture there. If you read zeros or twos, then, and you stop there, you are accepted. If at some point you read some 1, then whatever you read, you are rejected. And the other one, because they are kind of toy examples, is the Morse set. So this is for Cantor and for Morse. So these are the integer where written in base 2, when you sum the digits modulo 2, it's 0. So you have two situations when reading the digits. You are either congruent to 0 or 1. So you start there. Of course, at the very beginning, you did nothing, so you are congruent to 0. Well, I can read zeros, nothing will change. If at some point, so I give the digit to the machine, if you read some 1, then you will change the parity. Here, if you read some zeros, nothing will change. And you can change the congruence reading a 1. And, okay. So this is the automaton that recognizes your set of numbers. If you know the Morse sequence, you will see that it is completely related to this set. Yes, now, as I said, we can be interested in recognizing vectors. So just to mention the trick to do that, of course, when you write the expansion, they don't have the same length. What you can do is just add leading zeros here. You say 3 is 1, 1 in base 2. You add the 0, 0. And then your language is just natural ID is to take the pairs of the digits. And you can ask exactly the same question. And you can, for example, take the Morse set in dimension 2, which will be the sum of all digits in your 2 coordinates equal to 0. And you will have a nice tiling, which is not periodic, a nice set of numbers. So now I come to Cobham theorem. So I have a set of integers, and I choose 2 bases. And you see that the key point is that ask these 2 bases to be multiplicatively independent, meaning that if they have some common power, then k is equal L is equal to 0, or otherwise we can also say that log of q over log of p is not rational. This is a key point because it will be strongly used in the proof. So suppose that E is recognizable in 2 bases. It means here I write E in base P, I have a language, and an automaton recognizes this language. I write E in base Q, I have an automaton that recognizes this language. Okay. What happened? In fact, the only possibility is to be a finite union of arithmetic progressions. You cannot be anything else. So it's easy to show that in base 2, the even number are recognizable, but also in base 3, in base 4, in any base. It is an easy exercise. Just try. It's not difficult. But this direction, P and Q recognizable imply finite union of arithmetic progression, is difficult. The other one is easy. And I will give you a short proof in some special cases when I will have the second result of Cobham. And so the difficult part was a long series of more than 30 lemmas, very technical, where you can almost find nice steps to explain, to understand the general ideas that are behind. So a bit later, there is a famous book on automata written by Samuel Eilenberg, where inside he said, well, the proof is correct, long, and hard, and it is a challenge to find a more reasonable proof of this fine theorem. So himself, Samuel Eilenberg, inside his book, found another approach. I will give you his approach in some next slides. And so from the 70s, some people, quite a lot of people, try to understand more this result, to find new proofs, and you will see it went into a lot of directions, because to simplify, they try to characterize such sets in different ways, and it gives a lot of different direction to work. So he gave a second answer, which is that recognizable sets are not any kind of sets. In fact, he said that they are p-automatic. So what is it? Well, so let's continue with the power of 2. Maybe I should this was the automaton of the power of 2. Here I can read leading zeros, and I should. Okay. So what is first a p-automatic sequence? So here P2. It is I used to say a substitution, but it is an endomorphism here. I choose the alphabet ABC of the free monoid generated by the 3 letters ABC. Okay, so it means that you can go. This is defined on words, not only on letters. Okay, so the image of a word is a concatenation of the image of the words that compose this word. And you can iterate. So in this case, you can iterate, for example, on the letter A. And when you iterate, what happens, it's better to do it vertically. You maybe already have seen this. B, C, etc., etc. And what happens is that each time you obtain a common prefix which is longer and longer. So if you put the good topology, which is just infinite product topology, you will have the meaning of the convergence of this sequence. So let me write that this converge in some sequence X that sometimes is written like this. And in fact, with this topology is what? So this belongs to A, B, C, to the sequence, infinite sequence, or right infinite sequence over the alphabet A, B, C. Two sequences are close if they have a long common prefix. Okay, this is classical for subshifts. And with this topology, sigma is continuous. It's an easy exercise. Thus, you will have that X is a fixed point. So we say that X is a fixed point of a substitution or endomorphism. Sorry, I will always say substitution for this map there. Okay, and to be automatic, you need to be the image by a letter-to-letter morphism, which means here just letters are sent to letters. So A, C goes to 0 here and B to 1. So the image of by a letter-to-letter morphism of a substitution of length here 2. The length 2 means that here all images have the same length. If I add a C here, it will be no more a substitution of length 2. Okay, so it is a characterization of recognizable set because okay, just let me show you what happened. And I will leave you as an exercise to check it is true all the time. So just look at what happened. Okay, so this is a prefix, a long prefix of X. Okay, so this is the fixed point. Sorry, and maybe I can show this. So I pretend that when I use this map, then I obtain the indicator function of my set. So it's 0 when the elements do not belong to this set and 1 otherwise. So let's take the image and let's see what happens. So here A goes to 0. Let me also write the index there. So it's 0, 1, 1, 0, 1, 0, 0, 0, 1. And as you can see, so this is a power of 2 because it is index 1. This is a power of 2. Yes, so this is not. It corresponds to 3. It is 16, and it is so. This process with substitution gives you the indicator function of your set. It is another way to see such sets, and vice versa. Take any such sequence p-automatic, it will correspond to a set which is recognizable in the length of the substitution. Do not hesitate to ask questions. Those that are used to computer science maybe are familiar with that. Those that are not familiar with computer science maybe have difficulties to understand this, even if it's not so.
The number of letters corresponds to the number of states of the automata?
Yes. In fact, I forgot to say, the way to construct the substitution here, let's just write this, okay, and how to construct the substitution, and then you have to, with this substitution, you have to prove that it's solved, give a proof of the theorem. So, okay, start with A, and we look at the edges with the order of the digits. I mean, 0 is less than 1. So first, you read 0. Reading 0, you go to A. So I just write A gives A, and reading the 1, you go to B. So I just do that kind of silly thing. And then reading 0, I go to B. Reading 1, I go to C. And then from C, 0 goes go to C, and 1 go to C, so it's C. And just that, it is what you should use to prove this, and vice versa. So I let you this as an exercise because I'm not good as with exercises. Okay, so we say it is a two-automatic sequence, or just p-automatic in general. So just to continue the motivations, it's important to know whether P is recognizable. And Cobham did it in his second paper because it was easier to have this characterization I showed you to prove this. So I recall what Mark Policott remind you or show you in his first lecture, that the frequency of the prime numbers is n over log n. This is what will be used to show that the prime numbers are not recognizable in any base. In fact, you have the following result. So take a set that is recognizable, and using the characterization with substitution, it's not difficult to prove what follows. So, and suppose that, so the frequency goes to 0, which is the case here, and such that the set is infinite. So prime numbers are exactly, and in this statement, then it should satisfy one of the two following properties. So the first one is this one. So as you see, as here it's n over log n, and S is strictly between 0 and 1. This should go to infinity. Okay, but what Cobham showed is that if you are p-recognizable, it should be bounded. So it cannot, prime numbers do not satisfy this statement, and the other one is this one, and of course, it doesn't satisfy this statement either. So prime numbers are not recognizable. But we can understand this. As I said, we need longer and longer prime numbers to know if a larger prime number is prime or not. Okay, so it was the motivations. Now the summary of my two lectures. So starting from this Cobham theorem, a lot of work has been done, so I will try to make a survey, but I cannot speak about everything. And more or less in each area, I choose one spot, one theorem that I consider to be the best one or something like that. And as you will see, so it will go to logical stuff, algebraical stuff, geometric with tilings, combinatory conwords, etc., etc. And on Friday, I will show you a proof of Cobham theorem, not the original one because it's so long and difficult to explain the concept of the proof. But it's a proof of mind, and I consider that it is a rather simple once you have some background in dynamical systems. But otherwise, you could understand what's good with this proof is that the steps are clear, even if you don't know too much about dynamical system. For Cobham original proof, it's almost impossible. And then I will mention some open problems. And with all of this, if I have enough time, which is not sure, because there is quite a lot of material. So as I said, there are a lot of definitions, but there are three that are very important because they are, let's say, historical. It was the first one, and from them a lot of work has been done. So E is recognizable in some base P, if and only if, and I will define this later, it is definable in some arithmetic system. This is VP is a kind of evaluation. It is evaluation. But if you forget about this, you just have n and plus. It is called Presburger arithmetic. And what I mean by system, it is all the set that you can define with a formula of the first order logic with quantifiers. All the set you can define with that. Of course, as you can see, Buchy, but I think it's Buchy, we should say, was before Cobham. But rereading his paper, they discovered that it was equivalent. So I will say to you what is it later. So in the special case where P is a prime or power of a prime, there is a very nice result that you can read. It's very easy to read, of Kristol, saying that, okay, so here you have your set E, and you just consider your set E naively as a sum in this field. Okay, so you just sum the monomial over the set E. In fact, there is a more general version I will mention later, but it should be algebraic over the field of fractions of polynomial with coefficient in FP. I will give more details right after. And the other one, it was the attempt of Samuel Ellenberg to try to find a more readable proof. So he defines the p-kernel of the set. It means, so you should, so here is the variable of your sequence. It looks at all sequences. Maybe I can make a picture. So this is the characteristic function of E. You start somewhere in A and just look at every jump of pk. You just take the letter which is there, or the element. Okay, so the indicator function is a sequence of 0 and 1s. So this new sequence is composed with 0 and 1s. And what say the characterization is that the set of all sequences you can build with this process is finite. That's very strange. Take, I don't know if you know the Champernon sequence, which contains all words of length n. If you do that, you will obtain always, let's say, almost surely the Champernon sequence. So I will come back to this, but not too much later. So I continue the survey. There was also there was an extension in dimension D, Okay, so COBAM was in N. Here in D, you have the same. And again, the proof was not so easy to understand, and it was in Russian, so 2 difficulties. And so quite a lot of people try to find a more reasonable proof. And what I should say, so what should I say? So he worked in some logical stuff, and with some respect, yes, it was the best way to obtain this result. I mean, dynamical system can say things, but they can't say as much as this theorem, and I will tell why later. The problem here is to know what is a set E that you can define only using first order formulas with quantifiers, using integer variables and plus. That's not easy, and I will give some ideas of how they did. For logical, I imagine it is in, when you are doing computer science, what I will explain later, should be in 3rd or 4th years of university, I imagine. So what do we mean by definability in the logical context? E is definable if you can, I said, define it by a formula, but what is it exactly? So you see, definable is without the valuation, and P definable is using the valuation in base P. So the valuation here is the biggest power of P that divide N. Okay, so it returns you P to the K. First order formula, okay. What can you use? You can use integer variables to build your formula. You can use equality. You can use some functions that are given in your system, in your brackets. If you want to use other functions, you should prove that they are definable with a formula with the previous functions. Connectors, quantifiers, and a priori, you can't use constants, because I did not say that you could use a constant. So if you want to use constant, you should prove that constant exists inside your system. So if I remember, I can try to show that the constant 0 exists. Maybe you can find. So hopefully we are in N. In Z it may be different. How to show that you can use 0? 0 is just definable by this. This is the formula that defines 0. Now, okay, this is the formula. And what is the set, to be clear, what is the set of X such that phi of X is true? Well, this is just 0. Now, to show that 1, you can use 1. You should prove that 1 is defined by a formula. So what is 1? Hopefully we are in N. Alors, these are the X. Okay, so for all, okay, Y, let me try like this for all Y. It's X, but this is not defined. It should be greater than 0, and Sorry, I should have written it. And for all y smaller than x, y is equal to x. Okay. This is a formula, but two things. You should prove this exists and this exists. Well, I let you this as an exercise because otherwise it will take me too long because I did not. Well, it's easy. I just one ID, so it's not. Well, it just exercises, but you should build your theory, show that what you can compute inside. And this creates a difficulty to know exactly the geometry of the set that are definable or p-definable. So yes, maybe some examples of what kind of sets you can prove. So as I said, there is equivalence between p-recognizability and p-definability. So the power of 2 are 2 definable. Do you see why? Just some seconds.
Equal to v2x.
Yes. So it is a fixed point. Powers of 2 are fixed points of your valuation. So as you, for 2 definability, you have you can use valuation. Well, this is the formulas that define exactly the powers of 2. How to define it in base 4?
This is equal to x or x plus x.
Yes. Good. So you should be either a fixed point or x plus x should be a fixed point. Okay. This is, and you can, in fact, as the Cobham theorem said, once you are recognizable in some base p, you are recognizable in all its powers. So base here, base 4, base 8, etc., etc. Some other example. So here we are in dimension 3. So just take this, let's say, discrete line. As you see, it is definable. It is just definable. I mean, so it is thus definable in all base p, because I don't need here the evaluation. So it means I am in all these Presburger arithmetics. So I am definable in all bases. Okay, so this is a kind of set that correspond to finite union of arithmetic progression that were in the Cobham theorem. Okay, as I said, for Cobham-Semmelov theorem, the corresponding part of the, in dimension 1, here you had a finite union of arithmetic progressions, and here you have something else that for the moment are not, let's say, geometrically well defined. I don't remember at which point I should tell you something about that. Okay. So here, this is what I said. So it is ultimately periodic. Sorry, some time, because yes, maybe I should say this now. As we are jumping all the time between set of number and the characteristic sequence, suppose that E is equal to a finite union of arithmetic progressions. In fact, it is completely equivalent to have a characteristic function which is ultimately periodic. That it starts with something and then it is periodic, the period being the greatest common, the lowest common multiple of the periods of the progression there. Okay? And this, in combinatorics on words, we say ultimately periodic. So sometimes I say that the set of integers is ultimately periodic. Here. So maybe I should say something at this point. What happened in higher dimensions? So we have that. What is definability in a higher dimension? If and only if I will make the picture. So, yes, because sometimes, so I know several kind of problems where you have something in dimension 1 dealing with periodicity. You want to extend it to higher dimension, and what you do naively is to extend periodicity to translation periodicity. This is rather natural, I think, to, for example, result on tilings, where people, when they say it is a periodic, it means that there is a translation periodicity. And you see, in this case, up to changing some finite number of digits, this sequence is periodic. You change just this with with v, or you just delete them, it is periodic. But here, and this is really the logical stuff that prove that, because I tried with a colleague, Michel Rigaud, to do it by hand or by our tools, combinatorics. We did not succeed. So what is it to be definable geometrically? Well, inside some ball, it is not structured. But outside, there are finitely many, and it's true in all dimensions, finitely many hyperplanes. This, here cones. So that gives you cones, that divide the space into cones, inside which you see a lattice. Okay? So, like that. So in terms of dynamical system, it means that, okay, you have finitely many minimal dynamical systems, tilings, and each of them is a periodic periodic with translations. And the way they do it is very strange, very strange to me. So they use elimination of quantifiers. That is, first you have a formula with for all there exists, blah, 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 blah. What they first need is to check their formula. They need to eliminate quantifiers. And to eliminate quantifiers, what they need in this theory is they need extra functions. The extra functions they need are congruence function, congruence modulo some integers. So it is easy to show that these are functions that can be defined in the Presburger arithmetic. And once they have defined these functions, then there is an algorithm that eliminates all quantifiers. So they eliminate quantifiers, and at the end you just have conjunction of disjunction of formulas. So you just check these formulas, there are finitely many, to see if they are in your logical system. And that's the proof. And once you have this conjunction of disjunction of formulas without quantifiers, and you traduce this geometrically, you exactly obtain this. It is for me, kind of a miracle. And we try to do it combinatorially, but without success. So I stop with the logical stuff. And looking at my watch, I think I will continue with the survey on the second lecture. So about the result of crystal, some examples. So now take in base 2, so you are here in F2. Take, so each time put it there. So I remember that F, here what I call F e to the n is just this is just that. I say it is algebraic. When I give you the solution, or then it is as you are in F2, it's easy to check. Okay, because taking the square, you develop everything, but a lot of things are equal to 0. What remains is just that. And so when you do the first, I could have put here a plus, of course. What remains here during the difference is just the first term, and the first term will be eliminated with the x. So it is 0. Second example. Well, you can do computation. You have the equation. For Morse, it is a solution of this equation. Of course, the variables here are the y. Here's the trick, because it's not as easy as for power of 2. Remember what is Morse? Morse is just you sum the digits mod 2, and you check whether it is 0 or 1. So of course, when you multiply by 2, all the digits are moved to your right, and you had a 0, and so the sum of digits will not change. So you have this. But when you multiply by 2, move the digits, and you put a 1, so the sum of digits will change. So you have this, mod 2, of course. And once you have this, just don't forget that you are working in F2, and just computation. And as an exercise, I'll let you find what is for the Cantor integer Cantor set. And the int is not difficult because you are composed with 0 and 2 and no ones. So when you multiply by 3 and add a 0 and a 2, or 2, you stay in this set. But if you add a 1, you do not stay in this set. So this is what should be used. And when I mentioned crystal theorem, I said that, remember that here it was just an easy injection. You had the digits 0 and 1s, and you just send them to 0 and 1s in FP. But in fact, you can use any kind of injection. What I also did not say is that to be automatic, here I use a definition where I send to 0 and 1s, but you can send to larger alphabets, you will stay automatic. So just send your element of your alphabet where you want. It should be just a 1-to-1. Okay. Consider the two series you obtain, one, let's say in base Q, the other one in base P. In fact, they showed that they are both algebraic if and only if they are rational. And it is a direct consequence of Cobham theorem, because to be rational means that these sequences should be periodic. So you can use the characterization, in fact, of crystal, but to have these one-to-one maps, you need something more, but not a difficult work. So suppose it is algebraic. Let's do this direction. So it means that the coefficients are automatic. You use Cobham theorem. It means that, in fact, your sequence, of course, these are two different sequences because it is P and Q, but you can prove that they are both ultimately periodic. So in fact, these are something that repeat at some point, and just now rewrite your series, and you will obtain some rational series, some rational fraction. So it is just a consequence of Cobham theorem. And inside their papers, they mention why they were interested in such a result. This is a conjecture. I don't know if now it's known or not. I don't think so, but maybe. They wanted to give some answer of this. If one of these numbers, so you have some digits here, the digits let's say, are 0 and 1s. See, one of them is irrational, then the other one should be transcendental. And what they said is that if we work modulo some prime numbers, and this is true. But in the fields of real numbers, I think it's not known. Yes, so, and there were Jean-Paul Allouche that using Cobham theorem realized, it was in, I think in 99, that it gives a short proof of a result of Fatou, saying, so it is in R, that if you have an integer series with integer coefficients, integer, it's important because you want to send them in your field. Uniformly bounded integer coefficients. So this integer series is either transcendental or rational. And the idea is just, you have this series, you choose P and Q larger than the uniform bound, then you send the coefficient inside Fp and Fq. And what say Cobham theorem is that it should be ultimately periodic. Okay, so this is the corollary is just one line. And just a digression on transcendency, because I know from Gérard Rosy, that was one of the co-authors with Crystal, that he has something else in mind. It was to show that, so if you have a pure automatic sequence, so you construct with a fixed point and the image of a fixed point, and consider it as the digits of some expansion of some number in R, okay? So sum of the UK p to the k, p to the minus k, wanted to know whether it is transcendental or rational, to know what kind of number, algebraic number it is exactly. Okay, and so there were first an answer by Logston and van der Porten in the 80s, but unfortunately it was false. Then there was there is a correct proof by, I think it was Christian Mauduit, Sébastien Ferenczi, and Arnaldo Nogueira. I'm sure with Christian Mauduit, but the two others I don't remember. I did not check. But it was completely clarified in the framework of automatic sequences and generalizations of these sequences, recently by Adamczewski, Bujold, and Luca, that says the following. Well, in fact, I spoke about combinatorics onwards. So if you have an expansion of a number zeta in base B, you could be interested in the complexity, word complexity of your expansion. That is the number of words n that you see inside. Okay, you know, for example, that for pi, we don't even know if something about the letters. We know that all letters appear infinitely many times, but with which frequency we don't know. Okay, and I think I don't know if you can prove that all words of length n on 10 letters appear in pi for all n. So here, what is the result? Okay, take the expansion of zeta in base B. Look at all words, different words you can see here. And remember that on the two-letter alphabet, the number of words of length n is 2 to the n. So here I ask something very small. Okay, I say, well, but it is the first step, that you have significantly more than just n words of length n, or constant times n. What to do with that? Well, if you have such expansions, then you can prove it's easy. Either a rational number or a transcendental number. Sorry, no, if you have something which is not like that. Okay, and in fact, the automatic sequences do not satisfy this. If you take Morse, for example, take the sequence of Morse here. It was a 0 and 1, it's this one. Something like that. This counts the number in the characteristic function. You can prove it is I think I remember it is something like that. It is more or less 2 times n. So it cannot be algebraic because in this case it will be bounded. It is not periodic. It is an easy exercise. Thus it should be transcendental. Yes? And in fact, if you have a sequence x, if x in some alphabet is such that its complexity, number of words of length n, is bounded by some constant times n for all n, the constant k do not depend on n, then sum, let me say xn p to the minus n is non-periodic and different from u v is transcendental. And what is nice with this result is that if you take a fixed point of a substitution having primitive incidence matrix, but we don't care, in fact, it will always give you a transcendental number. Well, if it is not periodic, but periodicity can be decided. You can decide whether it is or not. So it means that take your favorite matrix. Let's say, for example, an easy one. Take this one, and now consider it as the incidence matrix of a substitution. So it is an endomorphism I will build. So in this column, I just describe the image of 0 in terms of ones and zeros. So there is 1, 0 and 1, 1. So I put this in this order. And here it means that I have 1, 0 and no 1. So I have this. There I have a fixed point. Something like that. Well, this is called the Fibonacci sequence, this one. Consider it as an expansion of some number in some base. It is always transcendental. So you have a kind of machinery. If you take another one, which is this one, well, but the thing is that, okay, you can, as alphabets are finite, images are finite, you just have finite, countably many such numbers. But you can also take this one, it is the Morse substitution, and create a number, a sequence like this. Apply successively substitution sigma I that belong to the set of these two substitutions, Fibonacci and Morse. Take the limit. It will grow, it will give you words bigger and bigger, each one being the prefix of the other one. So as you have uncountably many possibilities. They are all different. We can prove that. Then it gives you each time a transcendental number. So you have some easy process to create transcendental numbers. Because in this case, the complexity is as for For here, for Morse, it is a constant times n. So few number of words. This is, and I recall that yes, that what they expect is that when you are an irrational algebraic number, then the number of words of length n is b to the n. This is what I have seen. There is Jan Bujo and Boris Adamczewski wrote a lecture for some book, and they mentioned this. This is what they expect. I'm not specialist of that, so. Now something I can maybe skip and speak of that later. Yes, of course, just look at the first one. When you add 69 to 72, you can just change P recognizability by P automaticity and finite union of arithmetic progression by being ultimately periodic. Okay, so you had something in, let's say, arithmetic and computer science, and you obtain something in combinatorics on words, but it is just a translation. Just some other work. I will go fast, and and it will give you some maybe open problem. So we used a classical numeration system in base P, but maybe you know, maybe not. You can use a different kind of numeration. For example, take any sequence that is increasing, strictly increasing, so that the supremum of the here quotients is bounded. This is to ensure that your alphabet will be finite, because when you look at your process with a Euclidean algorithm, the digits are always less than that. So it is your alphabet. So if you take such a sequence, so your alphabet will be this one. You use the greedy algorithm, or Euclidean algorithm. You have an expansion, but you can ask exactly the same question. Okay? You can try to ask the same question. For the moment, we do not have P and Q. That the same question, what is it? You take E, you write with the Euclidean algorithm all the expansion of the element of E in the base you choose. And you say, okay, it is U recognizable if there is an automaton that recognizes this language. You should have in mind, maybe, if it helps, the Fibonacci sequence. So try to do a numeration, to use numeration. Of course, you should initialize too. And as it should be strictly increasing, I choose this. Well, here in this case, you know that this goes to the golden mean. So you will need two letters. And for this numeration system, everything is well known. It goes into this framework. So it is an open question, but maybe it is an exercise of some existing results. I did not have time to check. So it is just to show you the kind of question we can ask. Okay, so here I put linear, but just forget about linearity for the moment. Just suppose that the quotient goes to some numbers and that these numbers are multiplicatively independent. Is it true that we have the same kind of Cobham theorem? That is, when you are recognizable in both bases, then the characteristic sequence is ultimately periodic, which is your set E is finite union of arithmetic progressions. So you can see this as there were as an open question, but there were answers to that given by me first and then with Michel Rigaud. For Bertrand numeration system are classes of numeration systems that include Fibonacci stuff. The insides are all linear, but with some other properties. And abstract numeration system are numeration system for which you can ask for the help of some substitution. There is a substitution behind, and as I have a result on substitution and Cobham theorem that we have seen but I did not speak about, we can directly give something, a result. And this I will not speak about, and maybe I will stop there. And so next time I will just mention result on RD and then give a proof, and then give the open problems. Thank you.